In this set of videos, what we're going to start to do is to look at how do we find the center of an object, okay? And so if you look at this situation here, we've got, imagine this is something made out of cardboard. It's cut here and here, and then it's got a third side that's curvy. And the curve matches that relationship y equal x cubed, okay? So what we want to do is try to figure out where's the center of that thing. Okay. And the way we're going to do this is actually really similar. Well, it's identical, in fact, to how we did moments of distributed loads. Okay. Now, if you remember when we were talking about the moments of distributed loads and like trying to find out, where was the place it was concentrated? Okay, so let me kind of give you a little review here. So I got some kind of beam here and a load acting on this beam, and we said, where's the center of this thing, so that we could assume all the forces in one spot. Now, the way that we did that was we took our distributed load, okay, which is like some W of X, like this, and we integrated W of X, okay, with an X in there, okay. Now I'm going to actually undo that and make it the X a different color, just like this, okay. And then we had to divide that by Wx dx, like so, okay. And so hopefully that rings a bell for you. We're going to do the same kind of thing, okay? So if we do this like really generically, we could say we've got x, some function x dx divided by fx dx, okay? Now what that does for this is it gets us the average value for x is what that does, okay? Now, this part on the top, okay, there is a name for that, for when you're doing something like that, and that's actually where the term moment originally comes from. In physics, we use the term torque, and here, of course, we use the term moment. But that's where this comes from, and so this is what's called the first moment. All right, and I'm going to refer to that as x sub m, okay? There are second moments, which is when you do an x squared, and there's third moments, which is an x cubed, etc., etc. Now, we're not interested in those other things right now. I just want you to see and sort of get you back in the frame of mind of what we're going to be doing, okay? So we're going to be finding an average value, which means we'll use this moment integral, and then we'll need a total integral. Okay, so let me grab my eraser and see if we can undo, erase a bunch of this stuff here. Wow, you'd think there'd be an option for a big old fat eraser. Believe it or not, that's as fat as it gets. But, it's getting the job done. There we go. Okay. So what we'll do is we're going to find the total thing first, and then we'll calculate the moment thing. All right. Now, in this case, we'll have two moment things to calculate because we need a moment thing in X and we need a moment thing in Y. Okay. But let's go ahead and get to the total, which in this case is going to be the area. All right. And so what I'm going to do here is we're going to say the area, okay, is the integral of a dA. Okay. Now, I'm going to do it sort of in the style of Calc 3, which is to say we're going to do this as a double integral dx dy, okay? Now, I'm not going to put my second squiggle on there. You guys understand that it's there, okay? We'll put the second squiggle on here in just a second. So now I'm just choosing to do dx dy, which means I got to move in the x direction first and then in the y direction. You can certainly do it the other way around. So I'm going to show you this first, and then I'm going to show you kind of a classic Calc 1 kind of a way of doing that. I don't really care. You just need to get the job done, okay, whichever way works best for you. I think there's the most flexibility in this case right here, doing it this way. So I'm going to make this a little bit bigger. Whoa. Not that big. All right, so what I'm going to do then, all right, so we got to do our outside integral first. Wow, got problems with my hands. And we're going from 0 to 1. That's what my dy is going to do. And then my x, all right, I'm going to integrate from here over. All right, so I'm going to have a little strip like that. It's kind of the Calc 1 way of thinking about that, which is okay. There's nothing wrong with that. All right, but now my limit's going to go from 0 up to my function. Now my function is given as y equals x cubed. I got to turn that around and think of it as x equals something, okay? Because I'm going from over here, x equals 0, to, in this case, the cube root of y, okay? And so we'll put that in our integral here. We're going to come up to y cube rooted, just like this, okay? Okay, so I feel like I need to back off a little bit on that. Okay, so let's get some things going here. 0 to 1, that's my dy part. The dx is just going to give me back an x, okay? And so I've got my x here. My limits are from 0 to the cube root of y. So then I'm going to end up with 0 to 1. And I've got y cubed dy. And of course, then that becomes y to the 4/3. But I need a 3/4 on that because it's a 1 out front there. And my limit from 0 to 1, which means that just turns into be 3/4. Okay? Just like that. All right. Now, let me show you this using sort of Calc 1 way of doing this. And so what I'm going to do is I'm going to say, well, I'm going to look at my area, and I'm going to say my area is going to be my function dx from 0 to 1, okay? So if this works better for you, like I said, that's fine. It's fine. You really should be able to do it both ways, but I don't care which way you do. Now, our function in this case, we go from top to the bottom. So I'm going to have 1 minus x cubed. Okay, there's my dx. Oh, all right. So after I integrate that thing, I get x minus, it's x to the 4th, but I have to put in a 1/4 there. 0 to 1. And check out what happens. I get 1 minus 1/4, which is 3/4. Okay, so it works out either way. All right, and pick one and run with it. All right, that's my advice to you. Okay, so now what we're going to do, so I'm going to try to grab some of this stuff here. And I want, whoa, I'm out of control. There we go. I want to kind of get that out of the way just a little bit for you. Okay, and what we're really interested in here is that we came up with 3/4. Okay, like that. So what we're going to do now is we are going to, first I'm going to get a different color on here. All right. So what we're going to do first is we're going to calculate what I'm calling the x moment. Okay, so that looks like this. So I've got x sub m. Oh, that is not dark enough. I got to try again with that. How's that look? Oh, that's better. Okay, I think that'll show up pretty good. We'll try it here in a second. So I've got x sub m, and that's going to be equal to x times my function thing, okay? And in this case, that is my dA. All right, so what I'm going to have then is I'm going to have double integral x dx dy. Okay, so then we got to work out what our limits are. And so our x limit is going to go from 0 to cube root of y, still, just like before. And then our y limit is going to go from 0 to 1, just like before. Okay, so let's execute this thing. So I'm going to have 0 to 1. Now my x becomes an x to the 1/2. I got a half onto that. And my limits 0 to y 1/3 and a dy. And so I got my half. I'm going to leave that out front. If I put y to the 1/3 in for x, I'm going to end up with y to the 2/3. Okay, it's just going to multiply through. dy, we're going 0 to 1 like so. Okay, now I do the rest of my integration here. So I still have that half out front. My y to the 2/3 becomes a y to the 5/3. But I got to put a 3/5 out here to adjust for that. 0 to 1. So we're just going to be left with 3/10. Okay, that's my x moment. That is not the centroid. That's not the x center of the thing. It's not the average value for x. That's just my x moment. Okay, in order to get my average value, what we're going to have to do is take that, we'll write it like this, x sub m, or x average, it's going to be xm over the total. Okay, so we're going to have 3/10 divided by 3/4. Okay, the 3's are going to cancel, the 4 goes up on top, and we get 4/10, just like so. Okay, so that then is our answer for the x value. Now, we're just going to repeat that for the y position. Okay. So I need the y moment. So I'm going to have y dA on here, which is going to turn into this exact same integral. Well, not exact same integral, exact same limits. Okay. Y dx dy. All right. And, you know, again, exactly the same. 0 to 1, 0 to y to the 1/3. All right. So now we've got to integrate the x first. So I still have my y limits there. And I'm going to have a y dy on this thing. But let's figure out what's going on with the x here. Okay, dx just becomes an x. Okay, so I've got x from 0, y to the 1/3. All right, so that's my, what happens to my dx term in there. Okay, so now let's go on here with this. So if I put, so x, what I get back is y to the 1/3. Okay, so I'm going to have 0 to the 1, y to the 1/3. Then I can't forget these parts, y dy. So now I'm looking at 0 to 1, and that makes it y to the 4/3 dy. Okay, which becomes y to the 7/3 over 3/7. Okay, and plug it in our limits, just takes us to 3/7. All right, now again, that's not my y center of mass value, that is my y moment. So I got to turn that into a center of mass value, or a centroid value. So y-centroid is the y moment over a. So I've got 3/7 divided by 3/4. All right, and that turns into kind of a fraction we don't see every day. 4/7, just like that. Okay, so let me pull away just a little bit here. Okay, and then that becomes our value right here. Okay, so let's kind of take a look at this thing, big picture perspective. Okay, so when it says determine the centroid, that's the same thing as saying the average value. Okay, and the way we do that is we do this moment trick divided by the total. All right, so always find your total first. Okay, in this case, that's the area of the thing. You can do it by hook or by crook. All right, so use this powerful Calc 3 model or fall back to a Calc 1. It doesn't really matter how you do it. And then when we get ready to do the moment thing, what you'll be doing is you'll be plugging in XDA or YDA and repeat the same boundaries on your integral. However you did it before, you got to do that again. Okay, you just got to make sure you convert everything properly. Okay. All right. And of course, you could have done dy dx instead of dx dy. That wouldn't have made any difference in our final answer. Okay. Now, I know you've done plenty of this kind of thing in terms of your setting up your double integrals. I know you've done that in Calc 3, so I'm not going to spend really any time on it. Our boundaries are always going to be pretty easy. Okay, there's nothing really tricky or yucky here. Anyway, so you've got three problems on your homework, 3 fundamental problems that are like this exact one. Okay, let's just take a quick look at those. Okay, here again. Okay, so we're looking for a centroid. All right, so that means at some point you're going to have this xm over a, and you'll have y is ym over a. Okay, so you're going to find the area of this whole thing. That's what goes into your denominator terms. All right, and then your xm and ym are just going to be xdA and yda respectively. Okay, the next one, again, same idea here. Okay, anyway, by the time you get to that one, it'll be, you'll be like, oh yeah. So not too bad here. Not too bad at all. Don't know why my picture's kind of cut off there, though. There we go. Okay, let me go back, check my images here. Alrighty then. So we're gonna sort of do something just a little bit different in the next video, but it's all kind of part and parcel in the same sort of thing.